So the question is not easy to solve, but don't forget, Brett, that MS is the most successful disease in the neurological area in terms of therapies in the last 50 years.
The big progress has been first that the biology of myelinating cell is now better understood, and we've made a lot of progress in this part of the field.
We are now understanding that there is an intrinsic potential of regeneration, even in tissues like the CNS that we thought before could not regenerate itself, and this is important.
And we'll improve the results and we'll make step-by-step progresses. And I think, as Gianvito was saying, it's now a matter of years. Not decades, but years. Hello, I'm Bruno Stankoff. I'm a neurologist and a researcher in Paris in Pitié-Salpêtrière Hospital, also acting as the vice president of ECTRIMS.
Gianvito Martino, I'm a neurologist. I'm professor at the San Raffaele Scientific Institute in Milan, and I'm acting as scientific director of this institute.
And I'm Brett Drummond. You're listening to the ECTRIMS podcast, the official podcast from the European Committee for Treatment and Research in Multiple Sclerosis. Considering the enormous success that MS research has had in developing effective therapies that reduce relapses and slow disease progression in people living with MS, the next major step forward in the management of the disease involves finding treatments which can repair damaged myelin. It is thought that these therapies, if successful, would offer the potential to start to reverse some of the symptoms experienced by people living with MS. My guests in this episode, Bruno and Gianvito, have extensive experience in remyelination research. We will be discussing the barriers that prevent myelin repair from occurring in people living with MS, current research and trials in the area, and what the future holds in this space. Bruno and Gianvito, thanks for joining me.
Thank you very much.
Thanks for inviting us.
So I guess to start with, to really frame the conversation, when we discuss myelin plasticity and myelin repair, what are we actually talking about?
So I think you point very interesting and complementary concepts here. What we can call myelin plasticity is the fact that myelination of existing axons can still take place in adults. Following experience or learning, there is this possibility to add new myelin sheet to resculpt circuits in the brain and to reinforce some networks and the performance of those networks. One very excellent example has been the study of musicians who are training a lot to learn music, and they are reinforcing some white matter networks, and this is possible to quantify this by MRI, allowing them to perform better the music experience. And besides this, there is the concept of myelin, let's say, repair, which is not a perfect term. I don't know, Gianvito will comment on this. But this is not the repair of a myelin that has been partly destroyed and that will renew, but this is more a replacement of a myelin sheet that has been destroyed by a pathological process, such as the one in MS. And so there are new myelin sheets made by new cells that recapitulate some developmental stages and that will put a new myelin on an axon that has been demyelinated before this axon degenerates.
Let's add to what Bruno said. I do agree, of course, 100%, that until few years ago, we thought that the central nervous system where myelin is placed could not regenerate. We thought until that time that only myelin in the peripheral nervous system, the myelin ensheathing peripheral nerves, could regenerate, but not myelin within the central nervous system, in the brain and in the spinal cord. This is not true. We are now understanding that there is an intrinsic potential of regeneration, even in tissues like the CNS that we thought before could not regenerate itself, and this is important. what we are learning, and what was Bruno alluding to, is that we are learning the recipe that the nature has developed over 3 billion of years in order to repair tissue, including the central nervous system. And we are learning from nature which are the key relevant elements that might promote regeneration. The point is that regeneration is not occurring when there is a damage, and when there is a damage, everything is blocked. The recapitulation of the developmental programs Bruno was alluding to cannot be done as they should. They cannot be completed because there is a complete different environment, the embryonic versus the adult environment. But still there are molecules which could improve this, and understanding what the nature does, maybe we can try to find better mechanisms and better targets in order to foster this process.
I mean, it's really interesting, and I really like the terminology instead of repair, regeneration. I guess as a starting point in terms of MS, we know that early in the disease process, this can happen naturally in patients with MS, that their regeneration can occur. But this fails over time. Do we know much about why that happens?
So there are many hypotheses around this. Of course, as you are mentioning, time is playing a key role, and probably younger people are able to better repair or remind it compared to older ones. And this is not only the chronological age, but also, let's say, the biological age that may be influenced by the disease that may influence this process. So the time and the age and the disease stage strongly influence the process. But they are probably not the only processes that are involved, and there are additional factors that we have to take into account if we want to really understand why remyelination success or fail in a given lesion of a patient with MS. And these have been quite a mystery for a long time, and we had made a few progress, but there are still a lot of unknown mechanisms there. But we have made a few progress by developing new tools that are enabling now to investigate this not only on animal models, which are really good in repair their myelin, They are very good remyelinators, those animal models. But we have now new tools that enable to make this in humans, to investigate this during the disease in humans. And what we have learned is that people with MS are very heterogeneous regarding their individual ability to repair myelin or to regenerate myelin. And a few of them are able to quite well repair myelin over the disease course. And they have a better prognosis, but they're a minority. Let's say 20% of subjects are able to remyelinate quite well their lesion. And we are still seeing this at the post-mortem stage, meaning that this is good all over the disease course. And for other people, either they are bad remyelinators or they are, let's say, intermediate remyelinators, but they are not so good. And this is a very interesting point, because if we are able to understand now why people are able to remyelinate well in some cases, and to understand those mechanisms, we'll be able to promote remyelination for other ones who are not able to do it very well. And we have identified a number of processes or facts that influence this remyelination capacity. One is the inflammatory environment. And I think that Gianvito will go on with this after, but this is very crucial to keep in mind that MS is an inflammatory disease. And there is a very narrow, very close interaction between the inflammatory process, the immune cells in the lesions, and the ability to repair. And some activation state of immune cells are probably inhibitory for the remyelination process, and some other are more facilitatory. So there is a close interaction between the inflammation and the remyelination, and we cannot think about repairing, remyelinating, without targeting the immune system. This is a very important fact. A second is the localization in the brain and in the CNS. And we know that some areas are able to repair quite well, maybe let's say the optic nerves or some deep white matter areas, whereas others are less able to remyelinate well. This is, for instance, the regions that are facing the ventricles due to the proximity of the CSF. And they have an overall failure of repair. Whatever the person is a good or a bad remyelinator, there is a general failure of repair in these areas, probably due to a negative influence of the CSF and its composition on remyelination. And I would point a third point, and I will let after Gianvito complement this. But the third point is the axonal status. The axon is something that is very active in terms of biology. And the influx of the axon and the viability of axons is, of course, of key importance for the possibility to remyelinate. And if the axon is dead, or even it is not functional, probably the remyelination process will be inhibited. And those processes should be taken into account in parallel if we want to succeed to promote more the remyelination process in the lesion of those patients.
The question, Brett, is very simple. We don't know the cause of the disease. And this is the major issue. And of course, all those pending questions are very much depending that we don't know. We know there is some genetics involved, some environmental factors involved, but we don't know the cause. So we are looking into the pathogenesis of the disease. And as Bruno said before, we understood a lot of things in the last 20, 30 years. For example, that all the cells of the CNS are involved. Not only the myelin, not only the axon, but also astrocyte, microglia, all the cells. And they are talking each other. Some of them are protecting, some others are not protecting. For example, the immune cells and the inflammatory cells are not protecting. But which are the cells of the immune system which are protecting from those cells of the immune system which are damaging? This is something we don't know, we are trying to understand, but certainly is a global process. And this is the third thing, in which inflammation, of course, chronic inflammation, I would say, is very, very important. Certainly, we understood that we can do tons of myelin, but if we don't have any more axons, that those new myelin shouldn't sheet, there's no reason to make ton of axons, because of course we are taking into consideration what we so-call the axon glia unit. So the glia, the myelin is not enough if you don't have an axons which can be ensheeted, because only having a good ensheeted axon by new myelin can work. And therefore, this is something we understood, in particular in the progressive form of the disease, and probably which is the consequence that if we want to treat those patients, we should start from the beginning with remyelination, but also neuroprotective therapy in order to to save maybe axons as well, because we understood, as Bruno alluded to, that there are axons, for example, in the brain cortex, in the gray matter, which are damaged without involving myelin, at least at the beginning. So there are processes which are going in parallel, which are induced by inflammation, which hit both myelin and axons. So at the end, all the system is deranged. What we should understand more is exactly which are the good cells and the bad cells, but anyhow, the system is redundant, so the same cells can be good or bad at the same time, depending on the timing. Maybe in the beginning of the disease, they are acting as protective cells, but at the end, when the scenario is changing, they can be detrimental. So the question is not easy to solve, but don't forget, Brett, that MS is the most successful disease in the neurological area in terms of therapies in the last 50 years, because we have now 20, at least, drugs we can use in the very, very beginning of the disease, in which we have still ongoing inflammation, and those therapies are very efficient, but are not enough. We have been reached to one milestone, I think, very important milestone. Now we have to understand what happens after blocking inflammation. So blocking inflammation is not enough because the process is continuing, although at the lower rate, but it's continuing. So why this is not enough is there is something in parallel which is ongoing in axons, for example, in myelin cells, which is not strictly dependent on inflammation, it's just the consequence of the inflammation we had before, probably all of those things. So for sure, a very early diagnosis is important. Try to treat the disease very early, even for the axonal damage. I would like to repeat this concept from the very beginning, because the neurons are suffering from the beginning of the disease, and therefore try to follow the disease in different stages in order to be able to change eventually the therapeutic approach depending on the status of the disease. For doing this in the best way possible, of course, we need biomarkers. Bruno, of course, it's an outstanding scientist in the imaging field, for example, which is important, but we need also biological marker that we can much easier measure, for example, in the blood, in order to try to prevent a little bit those changing, and maybe during those changes to intervene with the right therapy at the right moment for the right time.
I mean, I think what's definitely come out of those responses there is a really clear understanding of why this is a very complicated endeavour to try and find therapies that are going to be able to regenerate myelin. I think what you've also both really illustrated, though, is there is confidence based on our experience with the existing therapies that we can make progress in this space. So thinking about that, what are some of the current approaches that are being investigated in this area?
Let's be a little bit optimistic. There are many approaches, and Gianvito was part of this. We had organized this year a kind of ECTRIMS focus symposium on this topic, and what are, the possibility and the study design and the outcomes that we should develop to promote remyelination trials. And let's say, for these new approaches, the big progress have been first that the biology of myelinating cell is now better understood, and we've made a lot of progress in this part of the field. And so moving from this, there have been a large number of compounds, of drugs that have been identified and that can promote remyelination in different models, either in vitro or in vivo and so on. And those molecules, let's say several dozens of molecules are now available, and they can be repurposed because they are already approved for other indications. And they can be investigated in trials. And the first trials have been conducted with, let's say, a success, even if it's a small success up to now. This is already a success because there is some biological effect of these molecules in the trials measured by visual evoked potential and tools like this, So those compounds are really promising. We have to go a little bit further, thinking about what we have said before, that those compounds should not target only the myelinating cells, but probably also have an effect on, let's say, neuroprotection or glial cells, to set up a positive environment for remyelination. But this is a very, very promising starting point. The second key fact is that we are now thinking about new designs because we are facing a new therapeutic paradigm. And Gianvito explained that we had a lot of success for drugs that target the inflammatory component. And this success was easy because the tool we have to use to monitor this activity of drugs was quite simple. We used MRI and we were counting lesions. It's kind of simple task. Of course, it's a little bit more complex as it. But as far as you had an effect on MRI, you had an effect on the relapses. And so the field was really going well with this simple paradigm. And we are shifting from this simple paradigm to another one where we have to find new study design to evaluate these emerging compounds to demonstrate that they will help patients and they will improve or prevent symptoms. And one of the key problem we can face about this would be how we have to think about the therapeutical lag. The therapeutic lag is that if we promote remyelination in a given area of the CNS, probably the benefit on neurons and even more on clinical progression may be delayed. And we do not know what is the precise time window of this, but it may take years. And this is a big problem. We have to find intermediate endpoint that will reassure us that if we have an effect on this endpoint, we'll have an effect on the clinical symptoms maybe months or years after. So I will come back after Gianvito about this, but this is a very important question because the design of the studies that we'll perform will critically influence the success of this field.
Yes, I agree with Bruno. Let me look into the future, the more future, I would say, because apart from the drugs that Bruno was referring to that we are now trying to develop, there are also the so-called advanced medicinal therapies which are getting into the field, in particular gene therapy and stem cell therapy, which are very interesting. For gene therapy in particular, there are those CAR T cells which have been used and are used for oncohematological diseases. So far, those are sort of cells which are targeting the bad cells in order to kill them in a sort of genetic way. And those CAR T, there are some patients which have been already treated, some MS patients with those new stream of gene therapy, and at least from preclinical work, the approach seems to be quite interesting. Although this approach is still part of the anti-inflammatory, let's put in this way, approach, and should be better used in the very first phases of the disease. But anyhow, it's an interesting story which is now concretizing. The second is stem cell therapy. We are now already using hematopoietic stem cells, for example, in malignant cases of multiple sclerosis. And to some extent, this can be considered a sort of successful therapy and a sort of potential approach in very, very specific cases, which are particularly vulnerable and malignant. This cannot be used so far in conventional, let's say, regular MS patients because it's too risky. Still, you have a risk, of course, death risk, life-threatening risk in performing this approach. However, we have also mesenchymal stem cells, which have been used already. Unfortunately, they didn't show to be very efficacious in patients, but there are still some space in maybe subgroups of patients in which those cells can be used, but still those are in the anti-inflammatory area. There are neural stem cells, of course. Phase 1 trial, 2 phase 1 trials have been already completed, so the cell seems to be safe, and this is important, but for demonstrating if they are efficacious or not, we need time, but still there are space, at least to try to understand if this is the case. In general, and there are also, devices, for example, in the neurotech field, which can be used, for example, prosthesis or exoskeleton, which can be controlled by brain-machine interfaces, which can be used, for example, to improve rehabilitation in this patient, although they do not try to block the pathogenic process. They are improving, for example, the ability of patients to walk and to move and to interact with the social environment and with the professional environment. There are several approaches. I must admit that those approaches are very promising, but are not yet a reality, unfortunately. We are working on it. This is still a baby science suffering from growing pain, but certainly what we can see at the end of the tunnel is that there are tools we can use, there are new approaches we can take advantage of, there are new avenues we can try to follow. And of course, I think I'm optimistic as Bruno because of course we are expecting to have much more to offer to our patient in the near future.
Maybe I can go on about the devices and the thing like that. I think this is a very interesting field, and it has been well demonstrated now that modulating the electrical activity of axons could have a deep effect on the remyelination process. And the pattern of electrical activity not only can enhance the remyelination process in a lesion or even outside the lesion, but also we know that it also influences the inflammatory environment. There are direct contacts between the axons and the inflammatory cells. And when you activate with a certain pattern the axon, you can modulate the inflammatory environment to become less pro-inflammatory and more permissive for remyelination. So it's a kind of broad approach. And we have now tools to neuromodulate those patterns. And we'll improve this because it's a very physiological way to promote remyelination. And it can start from, let's say, adapted exercise and coming to devices that will stimulate white matter tracts, either in the optic nerves or also in the spinal cord, because the spinal cord is a very important place, and we do not know a lot about remyelination in the spinal cord, and this is a gap. We have to understand better what happens in the spinal cord, because this is what will trigger motor problems and walking problems in our patients. So I think beyond pharmacology, beyond cell therapy, there is this emerging field with all those devices that can promote repair if they are implemented at the right time.
I think what's fantastic about that is we've obviously got a lot of different avenues that are being investigated to try and tackle this problem, and obviously the more different approaches we take, the more likely it is that we achieve success. But one thing that I want to discuss in more detail is around the trial design, because I think one thing that we all want to avoid is missing something that might work, not because it didn't work, but because the trial wasn't set up to measure success. And I think, thinking about the stem cell space, Gianvito, we've seen different trials looking at different routes of administration where we saw very different results if it was intravenous versus intrathecal versus direct injection into the brain. What are your thoughts around how we overcome some of the limitations with current trials, and what do you think are going to be the necessary steps here in terms of working out the best ways and the best outcome measures to conduct these trials to give us the best chance of finding successes? Not an easy question, but if anyone can answer it, I think the two of you can give it a good shot.
I can start with the cell therapy part of the story that you were, Brett, starting with, because of course it's very, very difficult to make a randomized double-blind placebo-controlled trial. But with the system, with the intrathecal system which was developed, unfortunately there are no data of the intraparenchymal injection in humans with multiple sclerosis of neural stem cells. They've been also injected so far intrathecally. The intravenous story was done in monkeys and mice, but was just preclinical, was a sort of proof of principle. Of course, in humans, the only way been used so far is the intrathecal one. So, giving this as a starting point, the problem with the cells that we have been trying to solve, and there will be a phase 2 trial, double-blind randomized phase 2 trial with neural stem cells intrathecally injected, possibly starting the end of the year next year, in which you can do a double-blind placebo trial, because once you inject the cells, you can do the sham as well, because you can inject 10 ml of CSF without cells and 10 ml of CSF with cells inside, and therefore this is possible. So this approach, I think, at the end can give us good result in terms of trial design. Regarding the hematopoietic stem cells, we had problem in the past to run double-blind controlled trials, mostly because of the induction phase. As you know, bone marrow should be wiped out before injecting the new one, and therefore that cannot be blind, of course, and cannot be done in a sort of placebo fashion, and therefore there were problems with that. But there are now new strategies in order to design trials in which you can compare efficiently both cells against no cells. And this is something with MRI, for example, we can try to solve. Unfortunately, the stem cells cannot be visualized with MRI so far. This is a great limitation. Of course, you cannot manipulate them too much, maybe inserting tracing, vital tracing, because this is something that could change the physiology of the cells that you transplant, and they can change the way they could protect. There are several problems, but still, using approaches which are different, we can try to solve them. Don't forget that one of the major problems is that when you set the preclinical experiment in mice, most of the time you don't think that at the end of the process you have to inject the same thing or to treat the same way humans, which are not mice, which are not monkeys. We are humans, which are different. And model can be useful, but to a certain extent. They are giving us some answers, but not everything, of course. And therefore, when you start something that you'd in a preclinical setting that you'd like to take into humans, you have to start from the beginning to understand what the humans need at the end, not the mice. This is one of the major mistakes. If you start doing preclinical work in a correct way, at the end there are less risky factor that you have to take into consideration. So I'm quite positive that we can also find strategies in order of running clinical trials in which you can easily compare new drugs or new treatment with, for example, placebo.
Yeah, let's say there are a lot of perspective in terms of trial design, depending on what we want to explore, and probably, of course, if we want to investigate the effect of a stem cell therapy or of a neuromodulation or of a drug compound. This will not be exactly the same design, probably because this is not the same effect that you expect and so on. However, the proof of concept studies, such as the one on clemastine, have proven that, investigating, for instance, the neurophysiological response in the visual system is already a starting point to include in the design, and it's sensitive to the repair process. So we have something in hand, we know that it can work, so it should be included in the design. However, we should still be open-minded and not focus on only one system and whatever. And let's say, even the clinical trial design is a research topic per se, and we have to make research on this to find the more appropriate, design we can implement for investigating the emerging proposal for remyelination. And this has been extensively discussed in our recent Focus Symposium, and not only, of course, we'll include the visual system and the neurophysiology, probably in phase 2 as the primary outcome. But we have also to think about more broad global measure using imaging that can have a view on the brain and even on the spinal cord, because we want not only to repair one system, but probably to repair the overall, if we want to improve the patient. So implement some advanced or performant imaging tools is a very key element. And finally, also biomarkers. If we had, fluid biomarkers that could reflect the repair process, it would be very useful because very simple to add to a protocol. So developing these trials is a research field per se. And for instance, in our center, we are now developing a new phase 2 trial for a compound that has been validated in our lab. And we, of course, let's say, take the visual system as the primary outcome. But we also included many advanced imaging tools from MRI, from PET imaging to capture the remyelination process. And we will also sample the fluids to develop biomarkers. And this kind of study not only focus on the effect of a given drug, but also about the outcomes that have been implemented and evaluated to really extract the one that could be the more useful in the future trials. And moving from this, I think that we have to go toward more platform trials, adaptive trials, comparing different approaches with, let's say a common framework of design, and that will enable us to compare different approaches and to identify the ones that are the more promising. And I think we are going towards this field, and if we are doing this well, in a few years, we'll be able to have really interesting proposal to promote remyelination in vivo in our patients.
We've sort of jumped slightly because I wanted to finish with asking a difficult question. Do you both think we will be successful in developing an effective myelin regeneration therapy? And if so, what's your best estimate in terms of time frames for that?
This is a $1 million question, of course, Brett.
It is. Unfortunately, I don't have $1 million to give out for it. But
not easy to answer, even because we are not prophet. We are simply scientists, and we cannot look into the future. Let me tell you this, that the excitement we are experiencing in the field of therapy for progressive MS form is similar to what we had when interferon beta was developed in 1980s, 1990s. I was in Chicago at that time, working there where the first trial was developed. And actually, I think that from that time on, actually, we were able to develop several therapies, as I said before. This excitement is continuing as we are experiencing now. I'm quite sure that we are going to get new drugs for treating even progressive MS patients. I'm quite sure. Not for being optimistic or just to look into the future in a prophetic way, but just looking at the data that we are reading every day on journals, data coming from outstanding scientists and colleagues, which are all around the world. Australia, France, Italy, everywhere, working hardly 24 hours a day to get to this point. So I think it will take a while. While, I mean years, certainly not days, not weeks, not months, years. But I'm sure that something will come out and will be better than what we have now. Probably not the end of the story, of course, but still a step forward, important for patients in particular.
Yeah, I agree that predicting the timing is always a very difficult and risky question. However, I agree that the more relevant point for me is that probably we have in hands the more relevant concept. So we have the concept. We have probably some tools. So we have many possibilities to promote a biological effect on, let's say, remyelination. And this is now the key question, how we can apply this concept to sensitive and powerful studies that will make the difference and that will accelerate the development. And I think one of our key goals now is to accelerate this, because we have a lot of knowledge about the inflammation, about the reaction of glial cells, about the axon biology, about the biology of myelinating cells, and so on. And so we may apply all of this to trials, but we have to accelerate this development to translate this in a powerful, let's say, design and realistic trials. So if we succeed to do it, we'll have very promising starting points. We have already them, and we'll improve the results, and we'll make step-by-step progresses. And I think, as Gianvito was saying, it's now a matter of years. Not decades, but years.
Well, I think that's a nice optimistic point to finish on. Bruno, Gianvito, I want to thank you both very, very much for joining me today. That's been a really fascinating discussion.
Thank you very much.
Thanks, Brett. Thank you very much for inviting us. It was a pleasure.
A pleasure for me also.
And thanks everyone for listening. Once again, I'm Brett Drummond, host of this podcast episode. I'm also co-founder of MSTranslate, an independent resource centre that aims to simplify the complex wealth of information about MS for the greater MS community. The ECTRIMS podcast is produced and hosted in collaboration with two key partners, MSTranslate and the MS Journal, a peer-reviewed international journal that focuses on MS, neuromyelitis optica, and other related autoimmune diseases of the central nervous system. The ECTRIMS podcast is supported by an educational grant from Roche, Alexion AstraZeneca Rare Disease, and other grant providers. Educational grant providers have no input on the podcast series content. You can read more about the topic of this latest podcast episode and more on the ECTRIMS website, ectrims.eu. Do subscribe to the ECTRIMS podcast on your favourite podcast channels and follow ECTRIMS on X, formerly Twitter, LinkedIn, Facebook, and YouTube.